Thank you for joining us today. My name is Jonathan Lewis. I help out on the committee for the Environment and Clean Technology Special Interest Group, and I'm going to be chairing this today. So this morning we have another presentation on the subject of PFAS. A couple of weeks ago we had Paul Nathaniel giving us a thorough overview of what PFAS is and the related chemicals, the chemistry, why we should concern ourselves with it, and some of the technologies and prospects in play and in development to deal with it. I'd like to thank Andy Leatt today for today's webinar. Andy Leatt, who you can see, I think you can see at the moment, waiting patiently, is the Technical and Development Director for CPL Purigen Activated Carbons. He's going to talk today about the use of activated carbon for the removal of PFAS. After completing his studies in chemistry at Cardiff Uni, Andy became interested in activated carbon while working at a lab equipment manufacturer who also produced small activated carbon filters. As he himself confesses, this was the only interesting part of the job. He moved into the activated carbon industry and hasn't looked back since. He's got over 15 years of experience in the application, manufacture, R&D of activated carbon, and well, you'll get the benefit of that experience now for about the next hour in what should be an interesting and informative talk. So without further delay, Andy, if you want to get to start off, over to you.
Yeah, great, thank you, Jonathan. Thanks for that kind introduction, and also thank you to the Institute of Chemical Engineers for inviting me to speak. So, yeah, I guess I'll get straight on with it. I think you can all see the title page and read it by yourselves. So this is the general agenda that I'm going to follow through today. Just give you a couple of minutes to look at that. All right, hopefully that's enough time. So some background to the company. CPL Purigen Activated Carbons is part of the Envica Group. The Envica Group creates sustainable value using innovation and technology to meet real-world challenges. It's an international group with interests in industrial technology and consumer businesses. Originally founded as Carbon Link in 1990, CPL Purigen has actually been through quite a bit of expansion via organic growth and acquisition, and ultimately forming CPL Purigen Activated Carbons, which is operating across Europe and the US. Somewhat unsurprisingly, given the company's name, our main product is activated carbon, and to support that business, we offer a range of equipment and supporting services. CPL Purigen has a number of well-established supply chains and operates multiple manufacturing sites in the UK, Netherlands and Spain. Onward distribution into neighbouring markets is provided through logistics centres in France, Germany and Italy. Being market leaders in a number of key segments is a direct result of the technical expertise provided by the large team of chemists, engineers and chemical engineers. And by combining this expertise with our in-depth industry knowledge, CPL Purigen's progression into innovative and sustainable technologies and products is well guided. So I'll just give a little background about PFAS for those who may not be aware. Per and polyfluoroalkyl substances, or PFAS, are a type of micropollutant. PFASs are, despite being classified as a micropollutant, a large, complex group of synthetic chemicals that have been in consumer products around the world since the 1950s. They have a chain of linked carbon and fluorine atoms. Because of the carbon-fluorine bond is one of the strongest, the chemicals do not degrade easily in the environment. PFAS is used in the aerospace, automotive, construction and electronics industries and are ingredients in various everyday products. Some examples are the use of PFAS to keep food from sticking to packaging and cookware, making clothes and carpets resistant to stains, and creating firefighting foams that are more effective. Unfortunately, over time, PFAS can leak into the soil, water, and air, and human exposure to PFAS is widespread, although variable by geography and occupation. Because PFAS tends to break down very slowly, if at all, people and animals are repeatedly exposed to it. The most likely exposure routes are by consuming PFAS-contaminated water or food, using products made with PFAS, or breathing air contaminated with PFAS. And multiple studies from around the world have confirmed the presence of PFAS in humans and animals. Even last night, I saw there was a new study that's come out from Jersey, where they found a very, very problematic level of PFAS in people. So it's really a very ongoing and continuously evolving situation. The concerns about public health impact of PFAS have arisen for these 5 reasons. Widespread occurrence, well, studies have found PFAS in the blood and urine of people, and scientists are not 100% sure if they cause health problems, although I understand that there is increasing evidence that they pointing to the fact that they do. There's numerous exposures where because PFAS is used in hundreds of products globally, there's just lots of opportunity for exposure. There's a growing number of types of PFAS. I mean, the UK Drinking Water Inspectorate have actually identified over 5,000 different PFAS substances already. And they're persistent, remaining in the environment. PFAS just stays there, and we don't know how long it stays there for. We haven't really seen it breaking down naturally, and the result of that is you get bioaccumulation, which is where people are taking in more of the chemicals than they're excreting. So you bioaccumulate. It's not great. Situation's not great. So for me, this is the interesting section now. So I'll just begin by asking what is activated carbon, and the answer is that it's a black porous absorbent material. A porous material is one which contains a large number of pores, and an absorbent material is a solid substance which can remove compounds from liquids or gases. So have a little look inside. Adsorbents work through the process of adsorption. This process is where molecules are being removed from the liquids or gases by binding them onto the surface of an adsorbent. The structure and underlying nature of activated carbon makes it a superior adsorbent because the porous structure of the activated carbon creates a vast surface area. A tablespoon of activated carbon has a surface area of around 9,000 meters squared. And for comparison, a football pitch is just 6,000 meters squared. That vast surface area provides a large adsorption capacity onto which molecules can be bound, and the unique surface chemistry of activated carbon enables it to trap and retain the adsorbed molecules, thereby removing them from the environment. Activated carbon's fundamental properties, combined with the adsorption process, make it a very special material and one which is well suited for the removal of pollutants from the environment. The manufacture of activated carbon involves 2 main steps: carbonation of the carbonaceous raw material at a temperature below 800 Celsius in the absence of oxygen, and the subsequent activation of that carbonized material. During the carbonization, most of the non-carbon elements, such as oxygen, hydrogen, are eliminated as volatile gaseous products through a pyrolytic decomposition of the raw material. The residual carbon atoms arrange themselves into sheets of a condensed aromatic ring system, which has a certain degree of planar structure. The arrangement of these aromatic sheets is irregular, which leaves free interstitial spacing between the sheets. These spaces may become filled with tarry matter or products from the decomposition process, or be partially blocked due to the naturally occurring disorganized structure of the sheets. One thing that I'd just like to add at this stage is that carbonisation does not produce products with a high surface area or large absorption capacity because the pore structure is not very well developed. Examples of carbonised material include charcoal and coke. Activation is a high temperature oxidation process, and steam is the most common oxidation activation agent. The objective of the activation process is to create a large pore volume in the carbon. This is achieved by creating new pores in the carbon and enlarging any pores formed during the carbonisation process. The structure of the pores and their distribution are largely determined by the nature of the raw material, pre-carbonisation steps, carbonisation conditions, activation conditions, and the activating agent. I would like to draw your attention to the SEM image on the right. The pore which has been circled in red is an example of a macropore, and these have a diameter greater than 50 nanometers. The pores which are circled in turquoise are examples of mesopores, and they have a diameter between 2 and 50 nanometers. And the pores in yellow are micropores, and these have a diameter smaller than 2 nanometers. So we are talking about a technology which is working at a very, very small scale here. In order to understand how fixed beds of activated carbon work in a real world setting, I am unfortunately going to have to go through mass transfer theory because you're going to need to understand it. So this is an overview on a macro scale of how a model fixed bed of activated carbon behaves in service. The line of columns across the top represents an activated carbon bed inside a filter and over time. Column 1 represents when fresh activated carbon is first brought into service, and column 9 is achieved when the entire carbon bed is spent. The yellow band present in columns 2 to 8 represents the mass transfer zone. The mass transfer zone is the volume within the carbon bed where absorption is occurring at that point in time. Absorption does not occur uniformly through the entire bed of activated carbon. So anyway, as the volume treated increases, you can see that the mass transfer zone is moving from the inlet, which is at the top of the bed, down towards the outlet at the bottom of the bed. Columns 1 to 6 represent the time when no emissions are being observed. Column 7 is the moment when the front of the mass transfer zone exactly matches with the end of the carbon bed and emissions start to be observed. Column 8 represents when the front of the mass transfer zone has passed the end of the carbon bed and the concentration of emissions will be seen to be increasing. And column 9 represents once the mass transfer zone has passed out the carbon bed, leaving all the carbon fully spent. Generally speaking, people use fixed bed activated carbon filters to meet an emissions limit or limits. And an important thing to realise is that the emission limit at a site is not necessarily attained when the front of the mass transfer zone reaches the end of the carbon bed. Generally speaking, the higher the emissions limit, the further past the end of the carbon bed the mass transfer zone can go. The mass transfer zone is affected by a lot of conditions, operating conditions, properties, but things that are particularly noteworthy are the temperature, fluid velocity, and indirectly, therefore, the empty bed contact time, and the overall fluid composition. In gas treatment applications, humidity is also a key condition. However, in the real world, every single molecule, type of molecule in the fluid stream actually has a different mass transfer zone, which leads to some complications. And I would like to take this opportunity to explain how this can lead to a phenomena where the concentration of a particular compound at the outlet is higher than at the inlet. And this is due to something called competitive adsorption. And I see it regularly, and often people find it very difficult to understand, so I thought I'd cover it. So competitive adsorption occurs because some molecules are better adsorbed than others. Molecules which are better adsorbed displace the more poorly adsorbed molecules, forcing them off the carbon surface and back into the fluid stream. Once these are back in the fluid stream, these molecules then need to be readsorbed, which happens further down the bed. Unfortunately, molecules which are poorly adsorbed tend to have longer mass transfer zones. As a result, these are usually the molecules which appear at the outlet first. And when the mass transfer zone for these more poorly adsorbed compounds reaches the end of the carbon bed, the desorbed molecules are no longer being adsorbed back into the bed either. And as a result, the concentration of molecules entering the bed combines with the desorbed molecules to create a higher concentration at the outlet than at the inlet. Right, so I've prepared a couple of case studies for us all to have a look at. Hopefully these will be of relevance to yourselves. So the first one is we had a drinking water, groundwater source that was being used for the supply of drinking water, and it was known to contain PFAS. The drinking water supplier believed that the PFAS compounds were specifically PFOS and PFOA at concentrations of 70 ppt and 14 ppt respectively. This was obviously a problem, and so the water supplier decided to undertake a study to identify what actions they might take in order to improve the quality of the water being supplied to the end users by reducing the concentrations of PFOS and PFOA in the supplied water. So to establish a best solution, they went out to multiple technology providers and contracted us and others to carry out some lab scale trials. In order to evaluate the suitability of activated carbon, a laboratory scale rapid small scale column test, or RSSCT, was put together. The use of an RSSCT was selected because it enabled us to significantly compress the time required to conduct the study, because the client needed the results pretty urgently, and we needed to get those done. Unfortunately, the feed water for the study was not provided, so we had to use a simulated raw water, and that was prepared using deionized water, PFOS and PFOA. We selected a carbon called FiltraCarb IChemE CH600 for the trial because it is an existing and commercially available activated carbon which is designed for the adsorption of small, medium and large PFAS molecules from water, while also simultaneously reducing the TOC or COD, how you term it. You can see the results of this trial on the graph on the left. The outlet concentrations were maintained below the detectable limit of 9 ppt for the entire trial. Based on the results from this RSSCT, the client then commissioned us to carry out a commercial scale trial to confirm the performance of the FiltraCarb IChemE CH600 at full scale on the genuine groundwater at the site. While the RSSCT was underway, the drinking water supplier also decided to do a more detailed water analysis, and they found quite significant variation between what they believed the water composition to be and what the actual water composition was. And the actual water composition is presented in this table on the right, and you can see that there is quite a significant difference. In order to provide a rapid solution for the client, a lead lag design, which is shown on the left was proposed, and that was designed to handle a flow of 75 cubic meters an hour, or 1.8 megalitres per day. Each of these vessels held 20 meters cubed of filter carb IChemE CH600 type activated carbon. The clean flow mobile filters, they allow urgent purification requirements to be met promptly, while also reducing and minimizing the capital investment for clients. This is particularly useful for sites where there is no existing treatment plant, or they can actually be bolted on relatively easily to improve the performance of other existing treatment processes. Very flexible. Now, hopefully, through the understanding of the mass transfer theory that I went through earlier, you spotted that using a lead-lag arrangement is going to allow clients to make better use of their carbon beds. And that's possible because once breakthrough occurs on the front filter, the rear filter can then be rotated into that front position, and then a replacement filter containing the fresh carbon is installed in the rear position. For this reason, we monitored the outlet water from both the front and rear filters. After 27 months, the front filter could be removed, the second filter rotation to the front position, and the replacement filter installed in the rear position. An important practical consideration is that the time taken to observe the second breakthrough, i.e. once you've moved the rear filter to the front position, will be significantly shorter than when the original fresh carbon was first installed. And that is, of course, because some of the second filter's carbon bed was already used when it was in that rear position. So let's move on to the second case study now. So this is a wastewater from a chemical plant. It had significant levels of COD and PFAS. The particular PFAS molecule was hexafluoropropylene, HFP. The site got their permit reviewed, and then they had to reduce their emissions. And they had an existing wastewater treatment plant, which consisted of physical and then biological treatment steps. The existing plant wasn't really able to treat the wastewater down to the required levels to meet their new emissions limit. So they had to act. The biological step was reducing the COD, but it was struggling to get it down low enough to meet their new limit. But it was also really completely ineffective at removing the HFP. So we worked with them to conduct a pilot study, and we did that by taking multiple clean flow HY1 filters, that's these ones on the left, and then filling different types of activated carbon into each vessel, arranging them in parallel, and evaluating their performance in order to compare them and find the right solution. After getting all the results, the client decided to go with the product called Filter Carb CC50R. That was their preferred option because it was the most cost effective and also had a low CO2 footprint. An interesting thing that was observed during the trial is that the activated carbon was reducing the COD level coming from the existing biological treatment works below the required emissions limit. And so with that additional information, the client decided not to carry out the upgrades to the biological treatment system because that was going to be extremely costly for them. So they didn't need to do that, and they were very pleased. So this graph shows the inlet and outlet concentrations of COD and HFP for the carbon filter. once the full-scale wastewater treatment plant was up and running again. The period I've covered is the summer, and the reason I've done that is that because really it's the most challenging period for the wastewater treatment plant at this particular site, and also it's the most interesting. The average operating conditions for the carbon bed are a flow of 130 meters cubed an hour. The inlet pH is 3.9 and the water temperature is 24 Celsius. You can see that there are COD inlet and outlet spikes around the 1st and 19th of August, and those are due to failures of the biological treatment system, rendering it unable to achieve its COD design outlet concentrations. Unfortunately, as a result of this, the carbon was overwhelmed and couldn't handle those elevated COD concentrations. They were just outside of the original design limit, although did still manage to keep them down a bit. What's really a particular note, though, is that throughout the entire period, the emissions of the PFAS, the HFP, were successfully managed, and that is despite any interference from the COD levels. Following the construction and implementation of this new carbon filters and the installation of the CC50R, that particular chemical plant is now able to comply with its emissions permit, and they continue operating the activated carbon filter successfully. Okay, so we've got spent carbon containing PFAS, and of course the question is, what do you do with that? Because you can't stick it in landfill, because it will then could leach PFAS back into the ground. So of course you want to recycle it. So the first thing to think about is spent activated carbon is a waste. Used activated carbon is a waste. You cannot get away from that. Waste is classified according to the application it's come from, and there are 3 classes of waste: hazardous, non-hazardous, and potentially hazardous, which is called mirror, slightly confusingly, but that's just what it's called. Waste from some applications will always be classified as hazardous, and an example of this would be spent activated carbon from flue gas treatment, which is 190110. Waste from other applications will always be classified as non-hazardous. An example of that is spent activated carbon used for the preparation of water intended for human consumption, which would be 190904. And then there are waste from other applications, such as sludges from groundwater remediation, which may contain hazardous substances, and those are this potentially hazardous. And in those instances, testing of the activated carbon, the spent activated carbon, is necessary to determine whether it's hazardous or not. The precise details of how to make that hazardous, non-hazardous assessment is given in a massive 180-page document called Guidance on the Classification and Assessment of Waste, Technical Guidance WM3. That's published in the UK by the Environment Agency, Scottish Environment Protection Agency, and Natural Resources Wales. It is very large and very complicated. And if you prefer not to have to read and understand all of that, you can get assistance with the classification of your spent activated carbon from CPL Purigen, as we have qualified in-house specialists who can support you with that work. So React-Sys is CPL Purigen's process through which activated carbon can be recycled and reused. This process significantly reduces the demand for virgin activated carbon and reduces environmental impact. users of activated carbon. CPL Purigen operates the UK's largest activated carbon recycling plant for activated carbon coming from industrial applications. The reaxis works as follows. So starting in the middle at the top, activated carbon is loaded into mobile vessels, which are delivered to the customer's premises or delivered to site to be filled into static filters. Then the carbon gets used, and following that use, the carbon becomes spent. Once spent, the mobile vessels are removed from the customer's site and replaced. That is the quickest and easiest way to replace the activated carbon. If mobile filters are not being used, then the carbon can be removed from the fixed filters. Following round, coming from the left down to the bottom center, the carbon gets returned to our vessel service center, and then moving over to the right, it gets transported onward to the reactivation center for reactivation. After the reactivation, the spent carbon has been recycled and is now known as reactivated carbon. This reactivated carbon goes back to the vessel service center, where it can be put into filters, ready for use again for more purification. Great. Some of you may have heard about reactivation and regeneration, and there seems to be quite a bit of confusion about the difference. Reactivation is a complex, high-temperature process involving several steps. The first step is drying to 150 Celsius to remove water. The next is thermal evaporation at up to 250 Celsius to physically desorb volatile compounds. Then pyrolysis and carbonization of non-volatile organics taking place up to 700 Celsius. And then the last step is gasification, and that's taking place above 800 Celsius in an inert atmosphere using an activating agent to remove carbonized material which was formed in that previous pyrolysis step. Regeneration is a low temperature process and is typically run between 120 to 250 Celsius. So that's something that you can do in your oven at home, provided that you can put up with the smell. It's much more simple. Regeneration is a good technique when you are looking to recover the adsorbed species, but you will not be able to fully reactivate the carbon. And regeneration does leave a large heel of adsorbed species on the carbon, and that can be up to 20% remaining. So you're only perhaps dropping a 10% mass loading, reducing it from maybe 30% mass loading down to 20% mass loading. So that regeneration has to be done very frequently, daily. So activated carbon used for the adsorption of PFAS from water has been successfully reactivated and put back into use following reactivation. It's already being done, and we're very confident in our ability to deal with the emissions arising from the carbonation and gasification of fluorinated organocompounds, including PFAS, and we have already conducted detailed work to study and confirm it. The off-gas from the reactivation kiln is sent to a thermal oxidizer before further treatment by our unique multi-stage gas scrubbing system. The wastewater from our reactivation process is then treated at our own on-site wastewater treatment plant. We're already safely, securely, and sustainably reactivating spent activated carbon that contains PFAS. It's already being done. So here's a summary of what I hope you guys have picked up today. Activated carbon is a powerful adsorbent, and it's capable of absorbing a wide range of molecules, including PFAS. CPL Purigen can provide high-performance gas and liquid phase activated carbons and the related equipment to deal with a wide range of applications, including PFAS removal from processed waste and drinking water. And activated carbon that was used to remove PFAS can be recycled and the PFAS destroyed using the Reactsys technology. This is an environmentally sustainable and circular solution.